My name is Buari, presenting research on relationship between comparative strength and modulus of elasticity of self-consolidating high-performance concrete incorporating Groundnut Shell Ash as SCM. The global trend of engineering material development in the last few decades is modification of ordinary concrete property with development of self-consolidating high-performance concrete by exploiting the benefits of high rainwater reducer or supervisor and supplementing cemented material. In this research, the residue strength performance and modulus of elasticity of Groundnut Shell Ash blended self-consolidated performance concrete was investigated, and Groundnut Shell Ash, which is GSA, as a supplementing cementing material. The use of self-consolidated globally in recent times is because of the inherited advantage of ease of workability, self-comparability, high strength and durability over ordinary concrete. Apart from CO2 emission in cement production, the use of GSA has a benefit such as less cement use, reduction in concrete production costs, reduces environmental pollution and improvement of durability property of concrete. So many researchers have worked on proving that GSA is a good supplementing cementing material, but it has not been used in the self-consolidating high-performance concrete. For this reason, this will examine the strength and the elastic behavior, which is used by substituting GSA at high volume between 0 to 40% at 0, 10, 20, 30, and 40%, and then to produce a self-consolidated performance concrete and characterized performance were measured after curing water for 7, 14, 20, 56, 92, 120, and 180 day hydration period to determine the compression and modulus of elasticity. The materials and method. Material used were ordinary Portland cement, Groundnut Shell Ash as a blender, as a binder, while river sand of 4.5 mm as a final aggregate, crushed stone of 12.5 mm as quasi-grade plasticizer, clean water as a mixing medium. An amorphous Class C ash was obtained and used for this research through controlled burning electric furnace at temperature of 650 for 3 hours. Consequently, the physical analysis, the moisture content, the gravity, and chemical analysis, the scan electron, and the SRF and SRD analysis were carried out at the University of Ibadan Federal Polytechnic in Nigeria. The design means to obtain a target strength of 40 megapascal at 28-day hydration was used to produce the concrete at water cement ratio of 0.36. These are the material that are used, and the table shows all the material, the Groundnut Shell Ash, the super plasticizer at 1.8, quasi grade at 960, white cement is 510 kilogram per cubic meter. So, result and analysis. The morphological and mineralogical characteristics of GSA as a core material shows that after studying the same image and the X-ray diffraction as shown in figure below, the same image reveal irregular surface in the feasible pore. The seasonally feasible pore will enhance the pore structure formation of concrete produced with GSA obtained at 650 degrees Celsius by improving the binding capacity of the component. So this is the image, the SR, the SEM of the Groundnut Shell Ash. So the compressive strength, the obtained results as illustrated in graph below shows that at early curing age up to 20% solution with value of 14.3 Newton per mm square, 18.6, 14.1, and 10.5, 9.8 for 0, 10, 20 respectively, up to 40% of GSA solution level respectively. The observed result was lower than similar research carried out by a researcher with 26, 36, 30, and 25 for 0, 5, 10, 15 solution level. Though the behavioral pattern may be associated to the effect of GSA in reducing the reactive powder of cement in early strength development of self-consolidated performance concrete. However, at 28, 56, 19, 120, and 180, as the curing age increases, there were faster strength improvement in non-GSA blended self-consolidated performance concrete than those control specimen And the result shows in table 2 reveal that 3 substitution levels of 0, 10, and 20% attain proposed design strength of minimum of 40 megapascal as designed. So the graph shows this is 7 day 14, 28, 56, and the effect of curing ages and compressive strength on the GSA blended self-consolidated performance concrete, the modulus of elasticity. The table below indicates that control specimen has a greater value of starting modulus at early curing age than those of blended self-consolidated high performance concrete. At 7 day, the value were 24,451 18 per mm square, 24,210, 23,568, 23,310, and 20144 for 0, 10, 20, 30, and 40 GSA replacement respectively. At 28 days, all the misses met the requirement as stipulated in NEPNAC and the STL of 18,080 per mm square to 30,000 maximum stipulated in the code, and that of 14,000 to 42,000 reported by a researcher. For instance, the value was observed to increase at 9.8%, 4.75%, 10%, 9%, 4.6% for 0, 10, 20, and 30, and 40 substitution level. So the graph shows that the effect of curing age on starting modulus of Groundnut Shell Ash blended self-consolidated performance concrete. The relationship and empirical relationship was established through mathematical regression analysis. The modulus of elasticity was calculated based on material component used in the progression. There are no specific approach meant for this. The expression in the BS8110 code as proposed was applied for determination of modulus of elasticity, and it gives us a regression model of up to 20% of 0.41, but from 30 and 40, you're having a regression that, and the graph shows the relationship between starting modulus and compressive strength of GSA blended at 0, 10, 20, and 30. In conclusion, the research work has revealed the importance of admixture, which is Groundnut Shell Ash, on the property of self-consolidated performance concrete compressive strength and modulus of elasticity, and it really depends on characteristics and property of cementitious material, aggregate, and curing ages. The compressive strength of GSA blended GSA is higher than the control with continuous strength development compared with that of control. The optimal level of GSA replacement for structural load fill point is 10% at curing of 28, having attained 122.50 of the design strength. The relationship between compressive strength and starting modulus of elasticity of blended self-consolidated performance concrete up to 180 days fitted into model stipulated in BS 8110. The characteristics and starting modulus of elasticity of development up to 20% replacement perform better and is suitable for progression of self-consolidating high performance concrete in an environment where strength, durability, and use of work is required. Thank you.
Are you ready for questions?
Yes.
Okay. We have several for you. When you replace cement with GSA,
all right.
How did you adjust the volume?
Okay. Actually, the SCM, which is supplementary cementitious material, was used. There was a table for the material that I display. The percentage was, the measurement were by weight. The component material were measured by weight. So it was batching by weight. So like now, 10%, the cement was placed at 510 kilogram per cubic meter. So the 10% of it is what is removed from the cement, and then the same amount in weight was replaced. back to cement to make up the total weight of 510 that is used as a proposed design.
Thank you. Other question, what were your standards of tests for compressive strength and modulus of elasticity?
Eventually, it was a destructive test using compressive testing machine. So, well, we have destructive and non-destructive, but destructive was employed to, based on the review of literature, major procedure that is employed. So that is what was employed in this similar research.
Okay. Another question, did you compare your strength versus modulus of elasticity and with the standard ACI equations?
No, I use BS8110 equation, though it's very similar to, but in Nigeria, the popular code that we employ is BS8110 when it comes to concrete. However, in addition with FNAC standard, because FNAC standard specify how self-consolidating concrete is designed.
Okay. The other question is, was a particular design of experiments used to come up with the formulations?
Come again?
Was a particular design of experiments used to come up with the formulations?
Oh, yes. Like the formulation can come in when, especially when you are predicting. So when you are predicting, but it's beyond, majorly this research is to compare, to look at modulus of elasticity and compressive strength, and at what level of substitution will this concrete be workable and up to expected proposed design. That is the major scope of this research. So actually, if the formulation, when you are predicting for further use, at least it can be used, if I get the question very correct.
Okay, thank you. I think we have come to the end. Are there any more questions?
I think that
That's it.
I cannot see more questions. So thank you, Dr. Buari.
Thank you very much.
Yeah, for the great presentation, very informative. The materials that you said